Okay, so in this chapter, we're going to step away a little bit from stoichiometry. We're going to start talking about how the atom is arranged, particularly with regards to electrons and how it leads to periodicity. But before we talk about electrons, we really do have to talk about how waves work. So waves have different ways of measuring. There's something called amplitude modulation, that's AM radio, that measures the height of the wave from the center to the peak. Then there's wavelength, and that's an important one. That measures the distance between the peaks. It's measured in meters or nanometers, and the symbol it has is an upside down Y. It's a Greek letter lambda. And then frequency, if you listen to FM radio, that's what that stands for, is frequency modulation. It's the number of cycles per second. The units it have are either hertz or seconds inverse, and I'll probably use an F because I can't for the life of me draw that thing. That's a Greek letter nu. If you have something with a large frequency, what that means is there's a lot of cycles or a lot of waves that go through every second, which means that the waves are very close together. It has a short wavelength, so it's an inverse relationship. Mathematically, we'll get to the calculation in a minute, but this is just going to show you what it is. Wavelength is the distance between peaks or corresponding parts on the wave or the valleys, okay? And if you can see, if I had a wave that looked like this, it has a lot more cycles in 1 second than this one does. It has 3. 1, 2, 3 cycles. This one would have 1, 2, 3, 4, 5, 6, 7-ish cycles. But its wavelength is shorter. So shorter wavelength equals higher frequency. And the relationship between them has to do with the velocity of light. So light is generally referred to as it's kind of electromagnetic radiation. The speed of light in a vacuum is this. The relationship between frequency and the speed of light is C equals lambda F. This is measured in meters per second, which means when you put in lambda wavelength, it has to be in meters, and frequency has to be in seconds inverse, so that the units match before you do that equation. This is what the electromagnetic spectrum looks like. If you have a relatively low frequency, you have a relatively long wavelength. And when you have a short wavelength, you have a high frequency. So the way electromagnetic radiation works is radio and TV waves tend to be the longest waves, microwaves are the next. Then you have infrared, which is right next to red on the visible spectrum. So the visible spectrum is this tiny little chunk. Then you have ultraviolet, which is right next to violet, X-rays, and then gamma rays. That's basically the 7 different sections. Visible light goes from about 680 nanometers for red light to about 410 nanometers for purple light. Very hard to see that purple, but some people can. So, sample calculation, light blue glow given off by mercury street lamps has a wavelength. That's wavelength. They want to know the frequency. So C equals lambda F. C equals, let's put in the number, 3 times 10 to the 8th equals, I'm going to just go ahead and straight away put it from nanometers into meters by multiplying by E negative 9, frequency. Solve for the frequency, and you get 6.88 e to the 14th second inverse. Okay, next one. What's the wavelength in meters of an FM radio wave with a frequency is given? So 3e to the 8th equals the wavelength times 97.3 e to the 6th. I'm going to convert it straight away into hertz. And the wavelength ends up being 3.08 meters. So a radio wave is about 10 feet long. That's a huge wave. Okay. So that's the sample calculations. And at the beginning of the 20th century, everyone believed that matter and energy were completely different from each other. Okay? Matter has mass, takes up space. Air people, tables, water, all of that has mass and all of it takes up space. Electromagnetic radiation, light, doesn't have mass, and it takes the forms of waves. And every form of light, if you remember the electromagnetic spectrum, has a wave with a unique wavelength and a frequency. And they don't have mass, and they don't take up space. The problem is, they were starting to run into some ideas, experiments with something called black body radiation and the photoelectric effect. And those two things kind of blew that idea out of the water. So, let me explain what those are. So, talking about the idea of quantum, a guy named Max Planck solved the problem. He was looking specifically at black body radiation. Black body radiation is similar to if you have an electric stove and you turn it on. You turn it on to 1 or 2, it starts to glow red. If you turn it on to 10, it stays red almost the entire time. And what they found is that if you turn that stove up to, say, 1,000, it gets to a certain point, and then it never continues to go above that. So the more energy you plug into it, it radiates light. It's a black body. It radiates light, but it stops at, I think it was ultraviolet, and it just crashes. And they couldn't figure out why. And so what they realized from there is that the energy that's released by a black body is only allowed to have certain amounts. It's only allowed to have what's called discrete amounts. They're called quanta. So the energy that's released is only in discrete values. Okay? So they thought, okay, we can kind of work with that. And then Albert Einstein was looking at this thing called the photoelectric effect. And he suggested that the light beam, and I'll show you what it looks like in a second, behaves as if it's not a wave, but it's a small stream of particles that form the wave. And he called them photons. So gold at the smallest level is an atom. Light at the smallest level is a photon. It's kind of an analogy, okay? And he said that the energy of one photon, one of those little tiny packets of energy, is Planck's constant times the frequency. H is Planck's constant. You don't have to memorize it. I'll give it to you. If I rearrange C equals lambda F, and I say, all right, F is C over lambda, and I plug that in, I end up with a different way of writing it. So either way is fine. Depends on what you're given. So this is what the photoelectric effect looks like. So bear with me. So you have here a chunk of potassium. And they know that it takes this much energy, 2.0 electron volts, to take one electron and make it fly away. Okay? If they shoot it with red light, they can shoot red light at it forever. And nothing will happen. Because red light has a very small frequency, therefore it has small energy. And if it has not enough energy to kick off that electron, then it doesn't matter how many red photons I shoot at it, none of them have enough energy to pop off an electron. Not one of those photons. If I move to green light has a little bit larger frequency, therefore a little bit larger energy on the scale. And this is the wavelength of green light. If I shoot the wavelength of green light, what happens is they notice that that electron goes flying off there with a certain velocity. And all the green light does that. Okay? The red light I could shoot at it for days and nothing happens. Shoot it at the green light and it always pops the electrons off. Okay? When I get to blue light, that even has higher. It's got the highest visible light, it's got the highest frequency and the highest energy. Which means when I shoot the blue photons, the electrons go shooting off with even more energy. And so that's the photoelectric effect. They couldn't figure out why red light wouldn't do it if you let it sit there long enough. It wasn't a matter of the red light being able to do it over time. Every little photon is a certain amount of energy, and none of them have enough energy to make the electron fly off, whereas all the green photons have enough energy, and all the blue photons have enough energy. And so each little photon has a certain amount of energy depending on its wavelength. Okay, and so from there, if we have waves, E equals h times the frequency, or hc over lambda, the energy of the wave is directly proportional to the frequency. High frequency equals high energy. And that's low wavelength, small wavelength. Okay. Then Einstein came up with this equation. You've probably seen that before, where E equals mc squared. M stands for mass, c is the speed of light. If I rearrange this equation and this equation and set them equal to each other, mass equals h times, or h divided by lambda over c for a wave, or mass equals h over lambda times velocity for matter. And so what this equation shows by doing this is called the de Broglie equation. It shows that waves with a wavelength have a mass, and that matter with a mass, has a wavelength, which is a weird concept. That's called the dual nature of light and matter. So waves and energy are not entirely without mass. It's really small, but it's there. And matter, has a wavelength. And again, it's really small, but it's there. And this relationship becomes more important when we start talking about atomic orbitals and electrons, because electrons have a very small mass, and they actually do have a wavelength associated with them. So to calculate the energy of electromagnetic radiation, all you have to do is use this equation or this one, depending on what you're given. I'll give you the constant. So we'll just do a couple of problems. It says calculate the energy of a photon with a frequency of this. So E equals HF. So the energy equals 6.626 E negative 34 joules seconds times the frequency, which is 6.74 e to the 14th seconds inverse. Those cancel. When you multiply it all out, you get 4.47 e to the negative 19 joules. Pretty simple plug and chug kind of stuff. It's not a lot of energy. Okay, if you guys remember when we were talking about joules and heat, 1 joule is hardly anything. This many joules is 18 zeros between the decimal and the 4. We're only talking about one little photon inside a wave. Okay, it doesn't have a whole lot of energy associated with it. So to calculate the energy of a photon with a wavelength, I'm going to use this equation. E equals hc over lambda equals 6.626 3 e to the 8th. And then I'm just going to go ahead and put 692 e to the negative 9. Put it in meters right away, because again, it needs to be in meters. Multiply it out, 2.87 e to the negative 19 joules. Okay, one more. Calculate the frequency and energy of a photon with a wavelength of this. This is red light. So frequency, 3 e to the 8th equals 656 e to the negative 9 times the frequency, and you get 4.57 e to the negative, or to the positive 14 seconds inverse. To put it in the energy, you end up with 3.03 e negative 19 joules. And that's for one little photon. The next question is about the closest we're going to get to anything with moles in this chapter is calculate the energy of a mole of photons. Well, that's just one photon. So if I wrote it this way, and I multiplied by Avogadro's number over 1 mole, that'll tell me how much joules per mole I'm going to get. So when I do that, it's 102,417 joules, or 102 kilojoules. Now we're talking some serious energy. Okay? Compared to this is significant because it's for a whole wave. mole of photons.